Hello everybody. In this video, we're going to go over a few different examples of hypothesis testing. We'll look at both two-sided as well as one-sided tests and learn how to do the hypothesis test. I was initially thinking I'd use Excel and R to show you the process, but I think the easiest way is to use the applet. So let's use that to solve these different examples. So let's read the first question. The mean length of lumber is supposed to be 8.5 feet. A builder wants to check if the shipment of lumber that she receives has a mean length that is different from 8.5 feet. Now, if the builder observes that the sample mean of 61 pieces of lumber is 8.3 with a sample standard deviation of 1.2, what is she going to conclude? Conduct this test at a 1% level of significance. Conduct this using the rejection region approach as well as the p-value approach. Let's unpack this question. We're told that the mean length of lumber is supposed to be 8.5 feet. Well, there's no word of sample attached to this statement, so most likely they're specifying something about the population mean. And the next statement says, a builder wants to check if her particular shipment that she's received has a mean length that is different from 8.5 feet. That is, she wants to check if the length is not 8.5 feet, but something else. And we are given that from a sample of 61 pieces, she gets the sample average of 8.3 and a sample standard deviation of 1.2. So what is she to conclude? Now, clearly, this is a question that's asking us to test the hypotheses. So let's begin by setting up the two hypotheses, the null and the alternative. Well, we know that the alternative is something that we want to prove, and the null is the opposite of that. We also know that the null generally represents the status quo, things as it is. So here, in this case, I'm going to say that the null is that mu is equal to 8.5. Okay, so the mean length is supposed to be a certain number, but then this particular builder wants to check if the mean is different from 8.5. So here, I'm going to specify that the alternative is that mean is not equal to 8.5. Okay. And we're told that x bar is equal to 8.3, and we're told that s is equal to 1.2, n is equal to 61. This information is given to us. So we've set up the hypothesis. So let's go ahead and check if our sample is giving us enough information to reject the null or not reject the null. Now, a quick check in step 1 is that we should also check if the conditions satisfy if we could use a t-test. Well, we could use the central limit theorem here because the sample size is greater than 30. And therefore, we could use the central limit theorem. And instead of a z-score, we'll use a t-score because we only have the sample standard deviation. So first step is satisfied. The second step is to decide on the alpha. Now, in the question, we're told that we want to test this at the 1% level of significance, meaning that our threshold is now at 1%, that is alpha, or alpha is 0.01. Fair enough. Step 3 is when we want to compute the test statistic. And the test statistic is also called t-stat or t-star, and that is given by x bar minus mu naught by s over root n. X bar is 8.3. Mu naught is the hypothesized mean value of 8.5, that is mu naught. So I'll put that down here. Divided by s over root n. S is 1.2, n is 61. So this is what we want to compute. Well, let me pull out my calculator and check what the answer is. So 8.3 minus 8.5 is minus 0.2. So it's going to be minus 0.2 divided by 1.2 over the square root of 61. And that turns out to be minus 1.3017. We could just take it to be minus 1.3. Okay. So that is our test statistic. Now, we're going to go ahead and look at the critical values or the threshold. So we're going to actually solve this using both the rejection region and the p-value approach. So for the first step in the rejection region, we are going to compute the critical values. So critical values will be where if we have our normal distribution like this, And if we have our standardized version such that we've drawn the t distribution, if I have t here, then, sorry, this will actually be 0, but let's not worry about it. We're going to be identifying our rejection regions at these thresholds such that the area to the right is equal to alpha by 2. This is alpha by 2, which is 0.01 by 2 will be 0.005. This area will also be 0.005. Therefore, this central area will be about 99% of the data set. So we have to find a t alpha by 2 with n minus 1 degrees of freedom, such that the area to the right of that point is 0.005. And once you find that point, we know what the corresponding point here will be. It will just be the negative of that. And I'm able to do that because of symmetry in the distribution. So let's go ahead and compute the critical values. So alpha is 0.01. Therefore, alpha by 2 is 0.005. N is equal to 61. Therefore, n minus 1 is equal to 60. So let's go and find our critical value, where you have t alpha by 2, n minus 1. Okay, let's find out what that number is. So for that, I'm going to switch to my applet. So here we have a t distribution. I'm going to specify the degrees of freedom to be 60. And I want area to the right. I want the area to the right to be 0.005. When I do that, turns out that this value that I'm interested in is 2.66. Okay. Similarly, if I want to figure out this area such that the point here, such that area to its left is 0.005, all that I have to do is do x less than equal to x and specify this to be 0.005. You'll get that this particular threshold value here is minus 2.66. So now let me go back and draw and show you what this is. So we see that this threshold value is 2.66. So essentially, we've identified this number. So this is 2.66. This point is minus 2.66. And these values are such that areas outside of these threshold values are equal to alpha by 2. Okay. So I identified the threshold values, that's the critical value. Now my rejection region is going to be precisely, let me just copy this and paste it here. So this region is my, or whatever I've circled in red is my rejection region. Now if our T star falls in any of these red circled areas, then we must go ahead and reject our null hypothesis. If T star is not in those circled or highlighted areas, but somewhere else in the middle, then we don't have to reject it. Now, our T stat value, our T star is minus 1.3. That's somewhere here. So essentially, this is our non-rejection region. Let me say non-rejection. And these are my rejection regions. And now because my T star is not in the rejection region, my T star value is what? It was minus 1.3. And 1.3 does not lie in the rejection region. Therefore, do not reject the null hypothesis. And that's my overall conclusion. Do not reject null. All that we did was we computed the T statistic. We identified the rejection regions. We saw that the T statistic does not fall in the rejection region. Therefore, do not reject the null. Now, if we were to compute the p-value in this question, how will we think about the p-value? Well, Remember that the p-value is where you're looking at the probability of getting a more extreme value than the test statistic. And because it's a two-sided test, you have to compute that extreme probability on both tails. So I have, so here is minus 1.3, okay? I have to find the probability of getting a value that is lesser than minus 1.3. So this is probability of t being lesser than minus t star. I also have, let me use a different color. I also have to look at the corresponding other tail and look at the probability of getting t greater than or equal to t star. And this plus this will be my p-value. Another way to do this is to just, and that is what exactly I've written down here. It is 2 times the probability that you have 2 times the probability of the region outside of the critical point. So if I focus on just this region, this area is equal to this area. So as long as I compute any one of these areas and double that will give me the p-value. And one way to write this is that the p-value is 2 times probability of t greater than the absolute value of t star, which is nothing but minus 1.3, or we could just look at probability of t being greater than 1.3. So now if I go back to my applet, so I want to look at area to the right of say 1.3, and this shaded region, the area is about 0.099. It will be 0.993. Okay, so now when I come back to my question, so when I compute the p-value, this will be 681.1986. That's my p-value. That is the probability of obtaining a value greater than, more extreme than 1.3 is about 0.1986 or 19.86%. Now the p-value is 0.1986, alpha is 0.01, p-value is greater than alpha, and whenever the p-value is greater than alpha, we do not reject the null. And therefore we conclude that do not reject the null hypothesis. So once you figure out alpha, both the rejection region and the p-value approach will give you the same answer. A key thing to remember is that if you get an extremely small p-value, then it is telling you that the likelihood of seeing the particular t-statistic or test statistic that you're seeing is very, very small. There is a very small chance that you can get a number like that or a number even larger than that. And that will label that as a very unlikely outcome. And therefore, that is evidence to reject the null hypothesis. Now, in this example, we are seeing a sizable probability of observing a particular number like our t-statistic. The probability of observing something like the t-statistic or more is about 20%. And 20% is way greater than our threshold of 1%. And therefore, we do not reject the null and we go with the null. And that's how you solve this two-tailed hypothesis test. In another video, I'll show you examples of a left tail and a right tail hypothesis test. So I'll see you in the video.